About yesterday, but today these are application problems.
Whoa.
Well, I sent enough down this row that you guys should have got them. Well, sometimes people have to actually get up. I don't know why I always have to do all the legwork. Michael. Oh. These are cool. Okay. So yesterday we talked about exponential growth and decay, like I said, but we're going to look at some application kind of problems today. We didn't do that yesterday. But before we do that, off to the side here, I want to make a little table.
Okay. I see where you're going.
Do you?
No, I don't.
I'm going to call this one day, and this one number of pennies.
Now I see where you're going here.
So day and number of pennies. So let's say you go home and whoever it is that you live with, you're like, hey, I would like to have an allowance. No big deal. Let's call today day 0, and you just give me 1 penny. And then tomorrow on day 1, you're going to give me 2 pennies because you're going to double the number of pennies that you give me every day.
You up a whole lot of money.
Okay, so then on day 2, if whoever it is that you're living with buys into this, they would give you how many pennies?
4.
4. And on day 3, they would give you 8 pennies. And on day 4, they would give you 16 pennies. And on day 5, they would give you...
Stop. You keep hitting my phone.
That's all I do? Yes. Sorry.
On day 5, they give you
32 pennies.
32 pennies. On day 6, they give you 64 pennies.
And then
On day 7, they would give you
$1.28.
Yeah, they give you $1.28. They give you 108.20.
$2.56.
And this is just what they give you on day 7. So not only on day 7 did you get 128 pennies, but you also got the 64 pennies from the day before that, and the 32 pennies before the day before that, 16 blah, blah, blah. So you have all of this money. So on day 7, do you feel like you're pretty rich?
Yeah.
Okay, so let's say this. So let's say this keeps happening. So
Keeps happening. They're gonna lose money.
I want to write an equation for this. This is exponential. A is the initial amount. It's what we start with. Does anybody know what our initial amount is?
1 is on 0. It's 1.
That's right. Our initial amount is 1.
But you don't have to write because.
Yeah, I don't have to write it, but I'm just going to. So our initial amount is 1 because that was day 0. That was the beginning of it all. We got 1 penny. B is called the growth factor. It's also whatever the ratio is every time, which is 2. 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. The other reason you can think of it as 2 is because these are doubling. Like 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So 1 is our initial amount. It's what we started with. 2 is our growth factor because we're doubling every time. And then this is what your equation would look like. So what I want you to figure out, and you need to use your calculator for this, on day 30, let's just say the month has 30 days in it. On day 30 of the month, how many pennies would you get? So in your calculator, see if you can figure out on day 30, how many pennies would you get?
You would have.
And just wait, don't say it out loud.
You should say it out loud. Like most of us.
So on day 30, this is how many pennies you should get. So we'd have a comma here, and a comma here. Can anybody tell me how many pennies that is? 1 billion.
1,773,000,000.
73 million.
73 million. 1 billion, 73 million.
753.
Would you just
Yes.
move it 2 decimal
So,
places over?
Hang on. 1,743,741,824. And then if I wanted to know how much that was in dollars, You can move your decimal over, or you could just divide by 100.
And this is just on the
This is just on day 30. So on day 30, okay, here's a comma, and here's a comma. So on day 30, how much do you get in dollars?
Oh.
$10 million.
$10 million. $737,418.24. That's just on day 30. That's not including what you got on day 29 and day 28 and day 27 and day 26, etc. Okay? So, of course, this would never fly with your parents, but anyway, it's kind of interesting. Well, they could be stupid for a while, and then eventually they're going to be like, what?
They'll get to that point.
So, if I put this equation in, like who, Anthony?
Like me.
Like who?
Like me.
Not like your Doctor Who.
Ryan, sometimes I just don't get you. So, this is an example of exponential growth. You can see that the number of pennies that you started with, it grew pretty slowly at first. But the more and more pennies you got, the faster and faster they grew. And so, eventually it gets to where this is going to show you scientific notation. So, since the number after the E this time is positive, you'd move your decimal to the right. But this is an example of exponential growth. It kind of grows slowly at first, and then it just takes off. So, I just wanted to show you something that was kind of exciting. All right, so we already know what growth looks like, and we already know what decay looks like, but I'm going to go ahead and put it down again. So exponential growth, that's what we just looked at, where our money starts off pretty slowly, but eventually, shoot, takes off.
Of course it does.
Okay, and then just to make up an example, y equals 4 to the x, that would be an example of an equation for exponential growth. It's exponential growth for two reasons. The exponent's positive and the base is bigger than 1. Okay, exponential decay, we saw this yesterday. It looks something like this. And the equation could look two ways. It might have a negative exponent.
Or it might have a fraction as the coefficient or whatever you call it.
As the
Base.
Base.
That one, that's what it's called.
or it might have a fraction as the base, like that. So something is exponential decay if the exponent is negative or if the base is a fraction between 0 and 1. I mean, we have fractions that are bigger than 1, but a fraction that's somewhere between 0 and 1. Okay, this next one has a typo, and this is the equation that we should use, but I want to explain why this is equation. So let's write it down, and then I'll explain where it came from. Okay, so this is what the equation is that we should be using, and I kind of want to explain to you where it all comes from. It's kind of like this equation here. Y equals AB raised to the x. So this 500 is the A, and A stands for the initial amount. Do you see how she started off investing $500? So that's the initial amount. That's the A. That's what she started off putting into her account. And then B is our growth factor. I want to explain where this came from. Do you agree that everything is worth like all 100% of its value until it either starts depreciating or it starts gaining somehow? Do you agree with that statement?
Maybe.
Okay, so like if you went to the store and, like the moment you got ready to purchase something, it's worth all 100% of its value, and either it will go down from there or the price could go up from there, depending. So you don't have to write this down, I just want you to see. So her money that she put in is worth all 100% of its value initially. Plus, she's also going to earn 5.25% in interest every year. So, on top of her money being worth 100% of its value, it's going to be worth another 5.25% after that. What do you get if you add 100 to 5.25?
105.25%.
Okay, and then do you guys remember learning that if you want to change a percent to a decimal, you move the decimal twice to the left? So, if I move the decimal twice to the left, do you get what you see right here?
Yeah.
Okay, that's where this came from. This is the growth factor, meaning your money is worth all 100% of its value, plus, on top of that, it's getting 5.25% annual interest. And then this is always written as a decimal, so that's why the decimal gets moved twice to the left. Okay, and then T just stands for the number of years. So we can do this two ways. I'm going to show you two different ways. So if I want to know how much money she has in her bank account after 4 years, what would I do?
Graph it.
I could do several things, but like what is not the 4 and the y? I put the 4 and the t. T is the number of years, and I'm interested in 4 years. So I'm going to put a 4 right there where the t is. So I'm going to show you 2 ways to do this. First, I'm going to do it in the calculator screen. So I'm going to type in 500 parenthesis 1.0525, close it, raised to the 4. You could put it in your calculator too, all 3 of you. That's why I wanted you to all have a calculator.
Yeah.
So this is one way I could put the answer in. Okay, and then did you get something like this?
Yeah.
So she put $500 in the account, and 4 years later, she has racked up $613.56. Now, this is just her dumping money in. She's not still adding on. It's not like she keeps going and putting more in and more in and more in. She just dumped the $500 in there, and then 4 years later, this is how much she has. Okay, so if I want to know after 18 years, what would I do?
You have to change the 4 to the 8.
Change the 4 to an 18. So I'm going to change the 4 to an 18 because it's interested in after 18 years.
Whoa.
And after 18 years, she has approximately $1,255.94 after 18. And this is just, dumping the money in and just watching it grow. Okay. How else could I have figured these answers out? Because I know somebody started to say something earlier.
Just by being amazing.
Could.
Okay, well you could put it in the y. You put the equation in the y equals.
Beautiful.
You just find it in the table.
Let's do that. I want everybody to do that too. So let's put the equation in the y equals. Now when you put the equation in the y equals, you're going to want it like how I originally wrote it, but instead of to the t, we'll put to the x. So when you put it in the y equals, we'll have the 500 parenthesis 1.0525, close the parenthesis, raised to the x. So I do need the x in the equation when I plug it in. Everybody understand what I just did there? Okay, and then I can go to the table. Josh. So I'm going to go to the table, and one of the things we wanted to know about was after 4 years. So if I go to when x is 4, is that what we got?
Yeah.
Okay, and then I wanted to know after 18 years, and after 18 years, is that what we got? And if you wanted to see what it was, like if I highlight that, you'll see a longer decimal, so that's how we know we can change that to 94.
Mine just says error a whole bunch.
You probably put something in wrong.
So I'm putting it for 18.
I didn't put that parentheses there, I promise. Yeah, go
Okay, and then part C. Part C says using calculator tables, which means what you see right here. Using calculator tables, determine to the nearest year when Josie's investment will exceed $2,000. So when does her investment exceed $2,000?
28 years.
28 years. So at 27 years, she was real close to the 2,000. At 28 years, she finally goes over the 2,000. So it takes 28 years for her money to exceed $2,000. Okay, number 2. The population of fish in a pond is increasing according to this equation below. In the equation, N represents how many fish, T represents time in years, E is a constant, and E is approximately 2.718. E is a number like pi. You know how pi is approximately 3.14? Well, E is an irrational number just like pi, and it is approximately 2.718. But I won't actually put 2.718 in the calculator. I'll use the E button, so I'll show you where that is here in a second. Okay, then it says, based on the equation, which of these is closest to the population of fish in the pond at the end of 10 years? Okay, so if I'm working with this equation, do you know where that 10 is going to go? Into the t. So I would have n equals 300. The e would still be there. I'm going to put parentheses. The 0.05 would still be there. I'm going to put a dot for my multiplication symbol, and then the t, I'm going to put a 10, and I'm going to close my parentheses. And I'm going to type it in pretty much just like this. This time I'm going to do it in the calculator screen instead of the y equals screen. Okay, so first I'm going to type 300. Now we need to locate Mr. E. If you look to the left of your 4, do you see a button that says LN? Mm-hmm. Okay, above LN in blue, do you see e to the x?
Yeah.
That's what you want. So go second LN. Go second LN, and then your e should pop up, and then I'm going to go parenthesis 0.05, then the times button, 10, close my parentheses.
Oh, smart.
And you get, which of this?
Yeah.
B. So,
Got lost. What did you click to get the E?
second LN.
Second.
What is that?
It's next
It's
to
all the way on the
4.
left.
It's to the left of the 4.
Oh, okay, thank you.
It stands for natural log. Did you get it?
Why is it called natural log when it's an LN?
It's just the way it is.
Stupid.
You know how it's like, you know, in your romantic languages where instead of you say the red car, you say the car red?
We don't.
Well, no, because we don't speak a romance language like your French and your Spanish. When you don't say the red car, you say the car red. Are you in Spanish or anything?
I am, but.
Oh, you haven't taken any Spanish?
The verb,
The
adjective
verb and then-
before the noun.
Yeah, it switched.
I got you.
Okay, so we started with 300 fish, and 10 years later we had 495. Oh, go little fishies. Yes?
How can we use the e there and not the other one?
In the first one?
Yeah.
Just different situations require different things. It just depends. Okay, this next one. The general equation for exponential growth or decay is this. This is very much like that y equals ab raised to the x. It just looks slightly different. Instead of the a, they use a c, and c stands for the initial amount, the starting amount, just like I told you a means. B is your growth factor, and the 1 comes from everything's worth all 100% of its value. What is 100% as a decimal?
1.
1. That's where the 1 comes from, because everything's worth all 100% of its value until it increases in value or decreases in value. Okay, plus R. R is the rate of change, and so if you ever see a percent, you're going to have to move your decimal twice to the left to get it in decimal form. And then T will be time. Okay, number 3, it says, in 2005, the town of Flat Creek had a population of about 280,000 and a growth rate of 0.85% per year. A says, write an equation to represent the population of Flat Creek since, and this is supposed to say since 2005. Okay, so I just want to write an equation based off of this equation we see right here, putting in numbers that I read, and I would have y equals, what do you think might go into the C?
280,000.
Yeah, C is our initial amount, and we start with a population of 280,000. So 280,000 is a C. Okay, parentheses, 1 plus. Now, R is your rate of change, and it's got to be in decimal form. So, do you see a percent sign there?
Yes.
So I need to move the decimal twice to the left, which would give you
0.0085.
0.0085. And then raised to the T. So this is just the equation that we can use to work with this problem. Okay, B says, according to the equation, what will the population of Flat Creek in the what will be the population of Flat Creek in the year 2015? And if I'm interested in the year 2015, do you know what I would change in this equation?
The T to
The-
10.
The T to 10. Because this is talking about since 2005, and 2015 is 10 years later. So I'm going to put a 10 right there in that T. Okay, so take a second and do it. Let's see what you get. And I don't care how you do it, if you plug the equation in the y equals and use the table, or if you plug it in the calculator screen, it doesn't really matter. Do, 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 do.
Oh, God. Not you.
Is somebody still without a calculator?
No, his calculator.
Yeah, totally.
There's one in the window over there. I don't know. Getting son.
Okay. Did you get that?
Yep.
Yay. Okay, so
Wait, 30 yeah.
So 304,731 approximately. So that would be the population. It started at 280,000 and 10 years later it's gone up to that. Okay, I want you to read number 4, think about which one you think it is, and then I'll call on somebody. So don't blurt it out. Mm-hmm.
Is it the same equation?
Um,
Oh, never mind. Never mind.
What do we do when we're done?
just sit there. No.
Why does it sound like some
Are you okay?
lady?
What?
Was that you making that sound?
What?
Okay, and what do you think?
D.
It is D. Because our sea otters are decreasing, we do want a minus, and so it is D. Everybody okay with that?
Yeah.
The sea otters were decreasing, so we needed a minus. Okay, this is a compound interest formula. It looks kind of ugly, but this is it. So A is our final amount. P is principal. This is either money you invest, or if you borrow money, it's the money that you borrow. So P is principal. It's either what you invest or it's what you borrow. R is your interest rate. Once again, it has to be in decimal form. So if you see a percent, you have to move your decimal twice to the left. N is how many times your interest is compounded in a year, and T is years. And we do have a typo in this too. So it says, when Jing Mei was born, her grandparents invested $1,000 in a fixed rate savings account at a rate of, this is supposed to say 7%, compounded annually. The money will go to Jing Mei when she turns 18 to help with her college expenses. What amount of money will Jing Mei receive from the investment? Okay, so let's try to write our equation. What do you think is going to go into the P?
1,000.
1,000. That's what she invested. That's the initial amount, called the principal. Okay, then I'm going to go parenthesis 1 plus. Okay, my rate. What do you think?
7%.
But as a decimal?
0.07.
0.07. Okay. N is how many times her money is compounded in a year. So if it says compounded annually, that would happen how many times in a year?
1.
Just once. If it said compounded quarterly, how many times in a year? 4, etc. Okay, and then as an exponent, my N is a 1. I'm going to hit a times, or I'm going to put a times symbol. And then what's T? 18. I want to see if you can successfully put this in your calculator and get a correct answer.
We gotta do a little dual thing. A dual. We gotta press the EX button.
No, there's no E in this. You guys try it and see what you think.
I feel like there's a catch to this one.
I don't.
Okay. That's cool.
Or not.
Got it.
What?
Crazy.
There could be more of a catch possibly if your N wasn't a 1. If your N was something other than a 1, I think you'd have to be even more particular about how you put it in.
Oh, were we supposed to like use brackets or something?
We'll see. We'll see if you get the same answer as me.
Is it supposed to look like so?
Well, that actually means pretty much everyone's gonna get this one right.
Not necessarily.
But will it work?
Yeah, that should be. Hit enter.
How you know? Exactly.
Yeah.
Unless you put it in wrong.
Oh, you have that backwards. It's 0.07 and then the divide by 1. Do you have it? And it should look like Now, I don't know if you put yours in like I did, so I was just going to talk about what I did here.
The thing could trick you if you didn't put the parentheses, the bad parentheses.
Yes.
Why'd you put 2 parentheses at the end?
Oh, I didn't even do that. That's what you're supposed to do.
So that's what I'm saying. Like, if the N wasn't a 1 in this problem, I think you'd have to put your double parentheses. Did some of you get the right answer without the double set of parentheses?
Yeah.
Okay, but I'm thinking if your N was something other than a 1, you'd need them. So I want to explain. This set of parentheses is around my fraction. I always put parentheses around my fraction no matter what. And then this set of parentheses is for everything that is getting multiplied with the 1,000. Because if I have a parenthesis here, I have to close it somewhere. So I have the parentheses around my fraction, and then I have the parentheses around the thing getting multiplied with the 1,000. And then I have I hit the exponent button, and then I have 1 times 18 in its own set of parentheses. And so I had somebody in my second period today who didn't have this as a exponent. They just had it like down here.
I almost did that, and I was like, nah, I'm done. So
Yeah, so that had to be an exponent. So after 18 years, she has approximately $3,379.93.
93 cents.
Okay, so I think you can get this done before we leave.
We probably can, but we're not.
That's why I was wanting you to get it done. Well, because you're going to want to use a calculator, and these calculators are kind of nice to use. They're a little bit nicer to use than your cell phone calculator.
perfect. That's exactly how I
Oh yeah, we should go on this.
I'm going to.
It's an inside joke. You want to get it.